Okay, so you've seen so far that a delta H of a reaction, this is the heat energy associated with a reaction, and we call that enthalpy. When there's a little circle up at the top, that means standard conditions, and so it's like 1 atm, it's 298.15. Also, if there's solutions involved, it'd be like a 1 molar solution. So heat energy. Remember that something can release heat, and so it can get really hot or can absorb heat. It's going to get colder and colder as it's trying to absorb more and more heat. So it's always a good idea to know if a reaction will produce or consume a certain amount of heat. One thing is to have supplies on hand. Like if it gets too hot, it could, usually reactions don't do what you predict they will do if it gets just way too hot. It turns into like just a tarry mess. Or then with cold, like reactions, we'll do things like absorb condensed air, like condensed water that's in the air. It just does stuff you don't want it to do. So if it gets too hot, you're going to want to make sure you have like something that will cool it, a cooling bath nearby. If it gets too cold, you might want to have something hot to give it some energy to keep it moving along. So there are reasons that you want to know what's going to happen. You also want to know if it's going to generate pressure because you don't want glass containers to explode. You don't want to seal things that are going to have issues with pressure. So you can check before you run a reaction, or at least make a pretty good guess. You don't have to be perfect on it if you're trying something new, but you make a good guess what the enthalpy will be, because we have measured tons and tons and tons and tons of these delta H's. So this is one kind. It's HF, which is heat of formation. It is still a type of reaction, but it's a specific reaction that only makes one thing from its elements. So that's one thing. That's what we're going to look at first. And the second thing that we'll be looking at is Hess's law. So whereas this is just like, it's like you take the little pieces of the reaction that have a little heat energy and you figure out what's going on in the reaction. And this situation, you take a few reactions and you flip them that already have full delta H reactions, and you kind of flip them around and you try to make them match the reaction that you have. So this is kind of like taking similar things and mixing and matching. So they aren't the same at all. They do different things, but they're kind of based on the same principle. The principle is that if something is producing energy or is absorbing energy, that energy is coming from somewhere. So let's look at the heats of formation reactions first. So this is the heat involved with forming 1 mole of a chemical substance from its elements in their most stable forms at standard temperature and pressure. So it's like standard conditions. You can find these in the appendices of the textbook, and I actually have a textbook pulled up right here to see. So you can look, there's like a big long list of these. Like I can kind of lightly scroll, and I don't know if you can get a sense. These are just some of them, some useful ones just for Gen Chem 1. You can see where that bar is on site. It goes on and on. These are alphabetically done. It's based on, the order is, it's based on the first element. So like there's the hydrogen, it's going to be the first element, fluorine. So it's going like that. So we'll come back to that in just a second. So let's work through what we mean by all of these different parts. So first we have 1 mole of an element. So if you look on the right hand side of these, you have something right here. There's a 2 there, so that's not 1 mole of a substance. So if we were going to fix this to be a heat of formation, we would have to make that a 1. And the way you do that is you do it by dividing everything, or multiplying everything by 1/2, which is the same thing as dividing everything by 2. So that's like saying 2, there's an understood 1 there, and then by 2. So that reaction would become H2 as a gas plus O2 as a gas, but there's a 1/2 in front, goes to H2O as a gas. You see the idea? So you can make this heat of formation. It's really important that it's just one of them, because we're going to use these numbers for like H2O, and we're going to use them in other examples and other reactions that have different coefficients. So this number has to be per 1 product. Let's look at the next one. Again, we have a 2 here, right? So then we do by half, 1/2, and then that's 2 divided by 2. So that would be 2 carbons as a solid plus 3 hydrogens as a gas plus 1/2 oxygen as a gas goes to C2H5OH as a liquid. Hopefully you're kind of getting the theme of this. So again, there's a 2 there, 1/2, 3 halves. So 1/2 Al2O3 as a solid plus 3 halves H2O as a liquid goes to AlOH3 as a solid. So you notice each of those just making one product. That's good. This one is making product. So far, so good. We have done the first situation, 1 mole. But it also has to come from its elements in their most stable forms. So now we're going to be looking at that left-hand side over there. And we'll notice, so hydrogen is an element. We'll just talk about the stable form at the same time. The stable form is like how you find it naturally at room temperature and 1 pressure. So we definitely naturally find hydrogen as a gas around us. Maybe in other places, I'm not sure. You might be able to find solid. It's going to be the gas phase. This is something that's almost always a gas. And then, so we're good on that one. And then we have oxygen. Definitely we find that as a gas. And we look at the next set of reactions. Carbon as a solid. Carbon is a solid. Hydrogen as a gas. Yes. Oxygen as a gas. So we're good there. Now look at this next one. This is not an element all by itself. It has to be an element. So this would have had to been like not this Al2 situation, but you'd have to have broken them apart into an Al, and this isn't the charged form. This is like just the full element plus oxygen as a gas plus, and then this one is also not split apart, hydrogen as a gas plus oxygen as a gas. And then you'd have that all balanced out. And so that one, it won't work as it is at all. And then if we look at the lower part of the chart section, we have bromine. We're good on that, and chlorine good, but bromine is actually not a gas. So you need to know this from the periodic chart. Last piece of information here. From the periodic chart, if this is our periodic chart, if you can't remember which ones are which, hydrogen is a gas. Helium and everything below it, those are noble gases, so those are all gases. And then oxygen is a gas. And I haven't squeezed it in very well. Fluorine is a gas also. Whoa. Fluorine is a gas also. So fluorine fits like right here beside. So fluorine and oxygen and nitrogen, those are also gases. They all fall right in that section there. Then for the most part, the rest of the table, it's a solid. So your pretty good guess on all of this is solid. The 2 other exceptions are we have mercury, that is a liquid. And then we have bromine over here, and that is a liquid. So that's a problem with this one. Bromine is not in its liquid form. So you would just say 1/2 bromine as a liquid plus 1/2 chlorine as a gas goes to BrCl as a gas. So they have to set all these reactions up with these conditions, and they wait and they wait, and then they measure the amount of energy that comes off the reaction. And that gives us a HF value for this single product.